So today we're going to talk about first-order linear differential equations, and this corresponds to section 2.3 of your textbook. First, we want to recognize what a first-order linear differential equation is. So recall that first order refers to the fact that the highest order derivative of the dependent variable in the equation is a first derivative. Okay, and the linear condition refers to the fact that the dependent variable and its derivative cannot be put inside of a function, cannot be put in a denominator, cannot be raised to a power other than 1. So those restrictive conditions force a first-order linear differential equation to have the following form: a of x dy dx plus b of x y equals c of x. So you can always take any first-order linear differential equation in x and y and put it into this form, where the functions a of x, b of x, and c of x depend just on the independent variable x. So it turns out this type of differential equation is special in that we are able to develop a formula to completely solve equations of this class. Now, the formula relies on an integral, so of course, we might not be able to actually completely get the solution because the integral might be difficult to obtain, but generally speaking, that's the best we could ever hope for in this class, is a formula that always works for any solution, for the solution to any differential equation of this form, a formula that involves integrals. So that's what we're going to be able to get. So in this video, we're going to go over the derivation of this formula. We're going to figure out how to solve this equation completely. So the first thing we're going to look at is a special case, and that's the case when the function b of x on the previous slide, this function b of x, is actually the derivative of that function a of x. So the differential equation has the form a of x dy dx plus a prime of x times y equals c of x. And it turns out that understanding this special case is going to be helpful in studying the general case. So if we think about it for a little bit, we recognize that the left-hand side of this differential equation is actually the form of the product rule for derivatives that you learned in Calc 1. So the left-hand side can be rewritten in the form the derivative with respect to x of a of x times y, right? Because the derivative of that product is the first times the derivative of the second plus the derivative of the first times the second. So that's exactly what we have there underlined in purple. So if we carry this through and we remember the fundamental theorem of calculus, we can integrate both sides of the equation, derivative with respect to x of a of x times y equals c of x. So if we integrate each side of the equation with respect to x, okay, and we remember that the integral of the derivative of something is actually just the something you start with. So the left-hand side just becomes a of x times y, and the right-hand side becomes integral of c of x dx. So now we can easily solve this equation for y, and we obtain y equals 1 over a of x times the quantity integral of c of x dx, and I also tacked on a plus c. That c is a capital C, different from the lowercase c there, just to sort of remind us that the constant of integration that you get from integrating the function c of x also gets multiplied by the term 1 over a of x. So this gives us a formula that solves the differential equation completely in this case. Y equals 1 over a of x times the integral of c of x dx plus c. Now, I drew a green box around that formula because that sort of is the completion of this special case. Don't memorize that formula, though, because we're going to now derive the more general formula that will work even not in the special case when the b of x function is the derivative of the a of x function. And the way we're going to solve the problem in the general case is we're going to find what's called an integrating factor. An integrating factor is a function mu of x that makes the left-hand side of the differential equation into a product rule. So we're going to take both sides of the differential equation and multiply by this integrating factor, this function mu of x, so that it makes the left-hand side into a product rule, and we're going to use then the method that we use in our special case, and we're going to find a formula for the solution in general. So how do we find a function mu of x with this property? Well, we start with the differential equation in first-order linear form, so it's of the form a of x dy dx plus b of xy equals c of x. First thing we're going to do out of the gate is we're going to divide through by the function a of x, and we're going to put the differential equation into what we call standard form, which looks like dy dx plus some function p of x times y equals some other function q of x. Now the function p of x is just going to be b of x divided by a of x, and the function q of x is just c of x divided by a of x. But we don't so much care what a of x, b of x, and c of x are in the next steps. All we care about are what the functions p of x and q of x are. So basically, the very first step in this process, you divide through by the function a of x, that's the coefficient of dy dx, if there is a function. If it's just the constant 1, then you don't need to do anything. And so you put the differential equation into this standard form here. Dy dx plus p of xy equals q of x. So that's the first step in the process. And now we don't know the function mu of x yet, but let's imagine, okay, suppose that's out there somewhere. There's some function mu of x that does what we want it to do, that takes the left-hand side of the differential equation and turns it into a product rule. So let's multiply our differential equation that we just put into standard form. Let's multiply it through by this as of yet unknown function mu of x. Okay, and so once we do that and we distribute the mu of x on the left-hand side of the equation, we get the following. Mu of x dy dx plus mu of x p of xy equals mu of x q of x. Okay, so if we find an integrating factor mu of x, that's what the differential equation is going to look like once we've multiplied through by this integrating factor. And so now we want to focus on the left-hand side of the equation, and we want to figure out what value of mu makes this quantity that I just boxed in purple into a product rule. So if we think about the product rule and what it says that the derivative of the product is the first times the derivative of the second plus the derivative of the first times the second. So this first term here, the mu of x times dy dx, that has to be the first times the derivative of the second. So if we want this quantity in purple to be a product rule, the only possibility is that it can be the derivative of mu of x times y. That's the only thing that would possibly make sense just by trying to match things up with the product rule. So the derivative of mu of x times y, just based on the product rule from Calc 1, would have to be mu times dy dx plus d mu dx times y, right? That's the first times the derivative of the second plus the derivative of the first times the second. So if we take this quantity right here, and if we match it up with the same quantity that we boxed in purple on the previous slide, which is mu dy dx plus mu py. If you notice back on the previous slide, that's the same thing that we had boxed in. The only difference is I've dropped the of x's just for clarity. So if we look, the first two terms, the mu dy dx, they match up perfectly. If we look at the second term there, we've got the y on the right-hand side, so those match up. So the only parts that we don't obviously match up are the d mu dx and the mu p. So that tells us that those two components must be equal. D mu dx must equal mu times p. So we can write that down as an equation that we obtained from all of this that has to be solved, has to be satisfied. D mu dx equals mu times p. And this is a differential equation. This is actually a separable differential equation. The function p is actually a p of x. It depends on x. And that's the one type of differential equation so far that we've learned how to solve, a separable differential equation. So we can solve this. Separating the variables onto opposite sides of the differential equation, we obtain d mu over mu equals p of x dx. Here mu is the dependent variable and x is the independent variable. And now we can integrate both sides of the differential equation. So we obtain the integral of d mu over mu equals the integral of p of x dx. Now that function on the right-hand side, the p of x, we don't know what that is. So we can't really simplify that integral any further. It's just going to be represented as integral of p of x dx. On the left-hand side, we do know how to integrate that. That integrates as an ln. So now we obtain the ln of mu equals integral of p of x dx. Now on the right-hand side, we technically should have a plus c. We have a constant of integration. We just want to find a value of mu that works. We don't care about finding every single possible general mu that works, any possible mu that works to make this left-hand side of our differential equation a product rule. So we're going to try to keep things as simple as possible. We're going to choose the c to be 0, so we're just going to omit it. So we have the ln of mu is equal to integral of p of x dx. The last thing we can do is we can solve for mu by taking e to both sides of the equation. That gives us e to the ln of mu equals e to the integral of p of x dx. The e and the ln on the left-hand side cancel out, and so we get mu equals e to the integral of p of x dx. So this is the value of mu that will make the left-hand side of the differential equation into a product rule. So mu equals e to the integral of p of x dx. Now let's see what happens once we found our function mu, how the rest of the problem works out. Because now we've done the hard part, now it's just going to be very similar to the special case that we considered at the beginning of this slideshow. So for this value of mu, our differential equation, which remember now is mu of x dy dx plus mu of x times p of x times y equals mu of x times q of x. So for this value of mu, this differential equation becomes the derivative with respect to x of mu of x times y. Remember that left-hand side is exactly a product rule for this value of mu. That's exactly what we were looking for. So the left-hand side is the derivative of mu of x times y, and the right-hand side stays the same. It's mu of x times q of x. So then following the method from the special case, we can integrate both sides of this equation with respect to x to obtain the integral of the derivative of mu of x times y dx equals the integral of mu of x times q of x dx. Again, remembering the fundamental theorem of calculus, the left-hand side of that equation just becomes mu of x times y. And the right-hand side of the equation stays the same. It's just the integral of mu of x times q of x dx, and we need to know what the specific values of mu and q are in order to integrate that. But now we're almost finished, because now we can just take and algebraically divide through by mu of x to get rid of the mu of x on the left-hand side and solve for y to obtain that y is equal to 1 over mu of x times the integral of this whole thing in brackets, and it's integral of mu of x q of x dx. And again, I put the plus c in there, the constant of integration, just to remind us that the constant of integration from that integral also gets multiplied by the factor of 1 over mu of x. If we forget to do that and we just tack on a constant at the end without the factor of 1 over mu of x, that's not going to give us a solution to our differential equation. So then in summary, let's talk about what are the steps for solving a first-order linear differential equation. Well, step 1 is you put the equation into standard form, which looks like dy dx plus p of x times y equals q of x. The second step is that you calculate the integrating factor mu of x using the formula mu of x equals e to the integral of p of x dx, where p of x is this function next to y that you got from the first step of your standard form. And then step 3, the solution to the differential equation is now given by the formula y equals 1 over mu of x times the integral of mu of x q of x dx plus c, where again we just have the plus c in the brackets there to remind us that the constant of integration from that integral also gets multiplied by the 1 over mu of x. So that concludes the derivation of the method of linear equations. We'll talk more about applying this to specific problems in another video.